It's just extra close.
It's fine. It's fine.
Just press OK. Stop. Okay.
Is that?
Go to Zoom. Go to Zoom once.
No, it has to.
And that cross also. And also from more, go to more and hide floating mapping contours.
Leading controls. Yeah. That's
Okay.
But it's not changing. Okay, I can also use the.
No, it's there.
No, it's there, but it's not working. It's okay. Don't worry about it. It's fine. It's fine. All right. Very sorry for the delay. I have some animations and I wanted them to work. So in the morning, we learned a lot about what gravitational waves are, what we are trying to detect. And now I will be talking about how you form the sources in the first place that you hope to detect with these detectors, okay? And in particular, I will focus on the astrophysical ways of forming these sources. There can be other ways to form these sources also, for example, primordial black holes, okay? Before I go to black holes, I just want to point out that I work at TIFR. And usually you do not see this picture of TIFR. Usually you see the building where we all work. And if you come out of the building and look away from that building, this is what you were greeted with. This is not a particularly good day. If you just come out during sunset, this is what you see. So since you were in one of the strongest universities of astronomy in India, please consider pursuing astrophysics career and consider TIFR along your journey, okay? All right, so we are all here because this happened, all right? And in 10 years, you have seen lots of these dots that just keeps populating. And very soon, so when this was first created by Aaron Geller, it looked so beautiful. And I think in 5 years from now, this will be very crowded, okay? But anyway, we want more and more dots here. And you all know that each of these blue dots are black holes that you have detected through gravitational waves, all right? Right, then the question is, how do you even create these sources? And that's what I will be talking about today. So initially, I will talk about some astrophysical formation channels. Then I will go to dynamical formation channel in particular, because that's very close to my heart. And I will tell you why it is close to my heart. And then I will take some very specific examples of types of sources with properties that you can only form through dynamical channels, and that is becoming more and more interesting as we see more and more of these sources using gravitational detections. And then I will mention some of the potential ways forward that can alleviate some of the uncertainties that are plagued today, okay? And that's just only my take on this. I'm sure there are lots of people all over the world thinking about potential ways forward. All right, so you want to create binary black holes that would merge within Hubble time, okay? So you start with two very high mass stars. Both of these will create black holes, all right? And then you want both of these black holes to emit gravitational waves and make a bigger black hole by merging. So it's very simple, yet very hard to happen in nature, okay? And these are the reasons. So Astro 101, if you have a blob of gas, then at some point gravity is pulling everything in. The center becomes dense and hot enough to start fusion that pushes everything out. And when equilibrium is maintained, this is called the main sequence of a star. If you have a very high mass star, the main sequence is short-lived, and then lots of crazy things start happening. So you create a core, let's say that this is the core, and that's usually called an envelope. So when it goes out of equilibrium, then the core contracts, the envelope expands. How much? Very, very dramatically, okay? So a solar mass star, or a 10 solar mass star that will create a black hole maybe, or that can grow all the way to 100 to 1,000 times the size of the star, of the sun, all right? Remember this, because this will become important in a few slides. And then, depending on the size, mass of the core, you get either a white dwarf, or a neutron star, or a black hole. All of these boundary values that I have given here, they are all, like, take it with a grain of salt, they all has plus minus something, all right? And then when the star goes from a star to a compact object, it loses a lot of mass, all right? So for example, this is 3 different metallicities, and you were looking at the initial mass of the star and the final black hole mass. As you can see, that what we expect is that a 120 solar mass black hole ends up producing only a 40-ish solar, 120 solar mass star ends up producing only about a 40 solar mass black hole. So that's a lot of mass lost, okay? Now imagine if you have a binary and you want them, both stars to create black holes, then both black holes to merge, then you do not want the binary to break in the first place, okay? So significant mass loss will expand the binary, it will become easier to break, and also when you form these compact objects, because of asymmetries of explosion, you can also get kicks. And these kicks can also very easily break these wide binaries, all right? So you need to save this binary from that. Then comes like a double whammy, all right? So you do not want the binary to merge before both of these stars became compact objects. So they need to be separated enough so that the envelopes do not touch. And then you do want the final compact object binary to merge within a Hubble time, okay? And these are kind of pulling to different directions, all right? So if you look at what is the rate of merger as a function of the same major axis, it's a very, very strong function of the separation. So if you just increase the separation, initial separation a little bit, it will take a very long time for it to merge. So just to crunch some numbers, if you consider 2 10 solar mass black holes and you want them to merge, that's the calculation I'm doing here, all right? So in the x-axis, I'm sorry you cannot read the numbers, it will not be important. And this is the in spiral time in gigayears, all right? And this pink shaded region is below Hubble time, all right? So anything below this line will merge and be interesting to us. And this is about 10 times the size of the sun, all right? Now, remember the size of the star before it becomes black hole is much bigger than that. So if you want to save it from that fate, you want the binaries initially, or at some in-between stage, to be separated here. And then some magic needs to decrease this separation to where they have any hope of merging. In binary stellar evolution, we have this magic. We call it common envelope evolution. Basically, if one star starts donating mass, and the star that is taking that mass cannot accrete at a fast enough rate, then all of this mass becomes a cocoon and engulfs both of the cores of the star. And then these cores basically spiral in because this is a dissipative system now. And at some point, the course, the orbital energy goes to the envelope, and the envelope can be ejected. All right? Serious uncertainties remain. All right? What is the viscosity? So that is the rate of in-spiral. And what is the binding that can convert the orbital energy to the binding energy of the envelope? By tweaking these two numbers, you can pretty much get any result that you want. Just to give you an example, by tweaking the, so you can kind of understand how it will go. So if you increase the binding between the orbital energy to the gravitational binding energy of the envelope, then you very easily eject the envelope, and then the final black holes will be stranded at a much higher separation. If you decrease the binding, they may merge within the envelope, okay? And remember, these two things that are now in spiraling may not both have become black holes yet, all right? Anyway, so that's what was the proposed channel when the first detection came from. This is called the isolated evolution of massive binaries, all right? And this is the magic that I talked about. So this was the initial separation. After the first common envelope evolution, it decreased to only about 43.8 times the sun's size. And then that's where the shrinking is, okay? There is no way you can create merging binary black holes through isolated binary evolution and avoid common envelope, except if you have very massive stars and they are tidally locked with each other, then the spin becomes equal to the orbital period. And if that is sufficiently high, then the centrifugal force can overcome the entropy barrier and mix the material throughout the star. So in some ways, you basically take stuff from the core, that is heavier atoms, and mix it to the envelope. As a result, there is no core envelope structure. The whole star slowly burn nuclear fuel and create heavier and heavier elements, okay? So since there is no core and envelope structure, these stars, if at all possible, they do not expand. The whole star then collapse, becomes a black hole, all right? People have done these calculations, and this is possible only in a very, very narrow range of parameter space, all right? So you need the companion mass to be rather large, and the orbital period needs to be within a narrow range. So this will be normal evolution because tidal locking will not be achieved, and this will be Roche-Lobe overflow because they are too close and the stars themselves cannot keep their masses with you, okay? So it's a tiny parameter space, and it's now, I think, quite well established that all the gravitational wave observations that we have seen so far, they all cannot be from this, all right? So, and for both of these cases, in addition to the separation reduction because of gravitational wave emission, if you also look at how the eccentricity of the binary evolves, so you will see that there is this minus sign. So if you start with a high eccentricity, by the time it merges, it emits away most of the angular momentum deficit, all right? So by the time it merges, it's mostly circular. And remember, LIGO is detecting the last phases of these mergers, all right? So it's kind of, so through isolated binary evolution, it's extremely hard to explain any measurable eccentricity. So the typical eccentricities, if at all, you would expect from isolated binary evolution is of order 10 to the minus 10-ish or less. All right. So there is another way. So this is gaining a lot of popularity. So the idea is that we know of AGNs. So AGNs are systems where a supermassive black hole is sitting at the center. It has a very massive disk around it, and this supermassive black hole is feeding from this disk. Okay? And there can be stars forming in these disks. These stars may be forming black holes, and these black holes may interact, and through a lot of different physics can create merging systems. All right? So the same reason it's interesting is the reason it's interesting is the same reason why it's very uncertain, because there are a lot of knobs. All right? It's very hard to create falsifiable claims in this scenario. So just to mention a few interesting physics that you can play with. So for example, you can play with Kozai-Lidov oscillations. So there is a supermassive black hole that combines with this stellar black hole, and you can do interesting triple evolution. Then you can have interactions confined within a disk for the black holes. And then you can do all kinds of exoplanet formation physics, like type 1, type 2 migration, type 3 migration, resonance trapping, all kinds of things that were interesting for planet formation. You can play with those for here also. And people are doing this. They are reinventing what has been written for in the context of planets here also. And interestingly, this is also the same mass ratio range. Supermassive black hole is very similar to a star to a planet.
Finding the center of the galaxy, not anywhere outside.
Right. So once you start localizing everything, maybe there will be some evidence or otherwise. Until then, I will stop talking about this. All right. Now, the other general method of creating merging binary black holes is if you create them inside dense stellar systems. All right. So for example, this is a picture of a globular cluster. They look fantastic. Even with a reasonably small telescope, you can look for them. Winter is a very good time. It's coming. If you have a nice, clear sky day, you will be able to see some globular clusters. They typically have masses in the range of 100,000. So this is only for the globular clusters in our galaxy. So 100,000-ish solar mass, roughly 10 to the 4 solar mass per parsec cubed central densities. Ages are between 9 to 12 billion years. Binary fraction doesn't actually matter for our context. Metallicity is low. Okay, so these are old stellar systems. And we see these in pretty much all galaxies that we observe. All right? So how do things evolve inside dense stellar systems? All right? So two stars come and interact with each other. So this is like a weak scattering. And if you remember your gravitational, physics like from class, this is a negative heat capacity system. So if one star loses energy, it will sink deeper into the potential. It will speed up, and now it has even more energy to lose. All right? And this, of course, is a runaway process. And this is kind of a mixture of two-body relaxation and dynamical friction. Two-body relaxation does not care about the masses. Dynamical friction cares about the mass. Both of these lead to what is called a mass segregation. All right? So if you have a system with a combination of, say, black holes that are typically more massive than the normal stars, then the black holes, being more massive, will just sink to the center. Okay? So this physical process is very similar to why dust settles on the floor. All right? Now, let's talk about timescales. How quickly does it happen? So, relaxation time and crossing time, well, let's not talk about it. So, the mass segregation timescale is related to the relaxation timescale by this factor. So, this is all stars, average mass, and this is the mass that you were interested in. So, let's say that this is a 10 solar mass black hole, and the average mass is about 0.5 solar mass. Then mass segregation will happen 1/20th the time of the relaxation timescale. And typical globular clusters are relaxed systems. So the relaxation timescale is typically 1/10 of the age. So a globular cluster will have enough time to relax the black holes and get them mass segregated. Indeed, when we do these simulations, we see exactly the same thing. So here I'm showing you what is called a core radius. So that is basically where most of the star is, highest density region. And this is the half mass radius. That is where the cluster contains half of its total mass. All right. And you see all these spikes. These are the effect of mass segregation of the highest mass black holes remaining in the cluster at the time. All right. So the most massive black holes sink to the center, do stuff, what I will come to later, and then it injects enough energy to come out of the core collapse. All right. And this keeps happening throughout the life. So when you bring black holes together, what happens? So these are now black holes that are residing in the highest density region of the stellar system. They find other stellar binaries or other binaries, and they interact strongly with each other. Okay, for example, here I'm showing you an example of a binary, that's the red things, interacting with a single star. Imagine that this is a black hole, and this is just a normal binary, had no black holes in the beginning. In the end, after doing this very complicated dance, you will find that one of the blue things ejected one of the red things and got into the binary. Why? Because the black hole is slightly more massive than the other stars, so it is energetically favorable to get the black hole into the binary. Now imagine that even if you start with all single black holes in the cluster, after two such interactions, an initially stellar binary will lose both the stars and will create black hole binaries. All right? So this is a three-body system example. There can be four-body systems, five-body systems, whatever. Okay? But the fact is, a black hole being slightly more massive will very easily come into a multi-body system, bound system. And then this way, you can easily form black hole binaries. So this is the process in a nutshell. So most massive black holes sink to the center the fastest. Black holes or black hole progenitors do not need to be in a binary at the beginning. Okay? So you can easily have single black holes and then form the binaries later. In fact, in our simulations, we find that none of the black hole binaries that we find in the end are primordial in nature. Okay? Now, these high densities allow binary black hole formation via exchange encounters like this one, via three-body binary formation. So three single black holes come, one carries the excess energy, leaving behind the other two bound, and via gravitational wave capture. If black holes come too close to each other, it will emit a burst of gravitational waves. If the burst is large enough, the total energy will be negative and they will become bound. What happens after? So now you have the binary black hole. Now it, of course, has a lot of binding energy. It's very hard to break it. So its orbit keeps shrinking via strong encounters, potentially making them merge within a Hubble time in the cluster. or maybe it gets ejected and merged at some later time. All right. So here is a dramatic example of results from a simulation. So we wanted to see how sensitive is it to form these binary black holes based on how many binaries you have in the cluster. All right. So what we decided is that we start the exactly same cluster. Initially, the high mass binary fraction was 1. And then other cluster that has initial high mass binary fraction 0, and we evolved them. So in isolated binary evolution channel, this will create binary black holes. This will create 0 binary black holes. Okay. Within a relaxation time, they match with each other. So a cluster just takes everything, mixes them up. All initial conditions are practically erased, and the final black hole binaries achieve properties that are allowed by the dynamical properties of the cluster. Okay. So you can form black holes only from high mass stars. So in one case, all high mass stars were in binaries initially. In the other case, all high mass stars were singles initially. So very quickly, if you have read Binney and Tremaine, know virial theorem, it might appeal to you. So you can write down everything based on the cluster properties. Okay. So the typical velocity dispersion is a function of the mass and the location. The escape speed is also a function of the mass and the location. Which binaries survive in the cluster if the binary binding energy is greater than this? So again, a function of the mass and the location. Which binaries get ejected? So the recoil speed is typically of order the orbital speed, which must be greater than the escape speed. And this basically tells you which types of clusters will create what types of black holes with what types of separation, and what will be the delay time distribution for these black holes. So if we do this, so this is the mass of a cluster, and this is the time scale of merger within a giga-year, then there are a few time scales that you can calculate. So this is the blue, the green is the mass segregation time scale. So the bigger the stellar system, the longer it takes to mass segregate. Then this red thing is the interaction timescale that turns out to be short enough that it doesn't matter. And then this blue thing is the in spiral timescale. So remember, if the escape speed is very low, it's very easy to eject the binary black holes before their orbits have hardened enough. Okay. And this is the sweet spot. And it turns out that the globular cluster mass function as we observe today peaks at the sweet spot. So it's not only that globular clusters are very efficient in creating these things, it appears that nature is the most efficient in creating the globular clusters which are very efficient in creating this. Okay. Yeah. Don't worry about the numbers here. Okay, so lots of sweeping assumptions went in. So Plummer's sphere, only single binary in a cluster, etc. So otherwise, it's not analytically solvable. Okay.
But in spite of the blue dot actually. So that is almost mass indifferent.
No. It's just it's very steep. It depends. And the steepness is coming from Peter's equation. So of course, from escape speed, you can relating the orbital speed to the escape speed, and that's the highest you can shrink the binary. But then the in spiral time is a very strong function of the separation, so that's why it becomes very stable. All right, so a few things that you expect, if you observe it, then you expect that it comes from a dynamical channel. Okay, for example, if you see measurable eccentricity in the 10 Hertz band in LIGO, okay. So this is an example of what you expect. I apologize for many of these lines. So they are basically different ways of creating these binaries. So there are quasi-Lidov triples, triples that are not active in quasi-Lidov. There are few body captures, single sibling, so all kinds of things. So what you really want to see is the following, that in principle, you can, let's say that this is where LIGO can detect it. You will see eccentricities or some fraction of eccentric mergers. If you go to lower frequencies, it will be easier to pick out eccentricities. If you go to even lower frequency, most of these dynamical systems will show measurable eccentricity. Okay, so astrophysically, if you're interested to figure out what is the formation channel of these things, it makes sense to go to lower frequencies and detect these sources there. Let's not talk about it now. So now the other thing that I want to talk about that you expect only coming from dynamical channels is masses is masses that are higher than some threshold. Okay, so these are called the black holes in the upper mass gap. Okay, so you do not expect a single massive star to evolve and create black holes that are beyond some mass. I just roughly made it 50. It's somewhere between 40 and 50. Everyone argues about it. And this was back in 2017. We made a bet. Okay, so these were the culprits. So this is me. This is Carl Rodriguez. Scott knows him very well. This is Daniel Holz, Chris Belczynski, and Ilya Mandel. Ilya Mandel was the moderator of the bet. And we said within first 100 detections, we will clearly see one black hole where the pre-merger mass, source frame mass, will be higher than this threshold. And even 50 didn't reach, and we found one. And both of these black holes were above this mass. Okay, so Ilya said that we won. I was supposed to get a nice bottle of wine. I could not travel to that particular conference because of visa, so I did not get the bottle of wine.
I will text him right now.
Do that. Do that. And of course, it's sad that Chris is not anymore with us.
Yeah.
All right. So why is that threshold even there? Okay. So it turns out that if you if the mass of the core becomes too high, then bad things can happen. It just blows up the whole star instead of forming black holes. Okay. Exactly where that happens is unclear because there are a lot of uncertainties in direct simulations and exactly how wind mass loss works out, etc. All right. Now, there are two ways you can form black holes above this mass threshold. Okay. Number one, imagine that you have created a binary black hole that merged and was retained in the cluster. Then this black hole acquires another black hole, and then this merges. Now, of course, this black hole that came from a merger of a previous binary black hole has no duty to be below this threshold. So you can very easily form mass gap black holes this way. In fact, depending on what the Barth spins are and how massive the cluster is, you can continue doing this and create a very high mass black hole. The other possibility is you have a high mass star and that merges. So this is a star, not black hole, merges with another star, and it creates something that looks very peculiar. So it has a low core mass with a very high envelope mass. So the core mass is below the threshold, so it does not blow things up. It forms a normal black hole, but it had so much envelope that this envelope then falls back onto the black hole that you just created and just grows the black hole mass beyond the mass gap. Okay? So we wanted to test out where these two different processes are most active, what are the properties, and how things work. Okay, so this was my graduate student Ambrish. He has graduated and moved on. That's still in academia, but left me. So this is a lot of details that you do not need to know. What we basically looked at, we modeled a bunch of clusters with exactly the same stellar population, and we wanted to see. We simply changed how many of the massive stars remained in binaries, and we looked at exactly what matters. And you can actually, I will skip some of this. All right. So basically, what you were seeing is if the high mass stars initially are in binaries, then it increases the decreases the mass segregation time scale just by the 1 plus mass ratio. And that can create a bunch of these high mass black holes. But after about a relaxation time, they match with each other. So the blue and the orange dots are from the two extreme cases. And what is really interesting is that the local observations are telling us that high mass stars are often in binaries, okay? But we do not know whether that is true everywhere. And if we go to a bigger horizon, so if we start detecting things beyond, say, redshift of 1, we will see a very clear difference in the number of black hole mergers above this high mass, the black hole mass threshold. We will also see effects of that in the mass ratio and sharp mass distribution. Okay, but you have to be sensitive and start detecting beyond, say, 1-ish redshift. So these are some of the uncertainties. The purple, I think, are the more immediate and more affecting. So one of the things that plagues us a lot, that is, we do not have a good way to connect compact object properties to the properties of their progenitors. There is a lot of uncertainty there. And the other thing is, although we understand exactly how dynamics actually take stars and evolve them and form these binary black holes and so on, we do not know how to put the t equals 0 of a cluster's life in the cosmological redshift scale. Okay, so that's basically the cluster formation history over cosmological redshifts. So the first thing, I think Gaia is going to be fantastic for that. So basically what Gaia can give you are the following. So imagine that you have a black hole and a star just going around. You may be able to detect the astrometric motion of this star. Or if this there is tidal deformation, then periodically the star will subtend a different surface area, so that will create a photometric modulation if you just keep looking at this star. Both of these Gaia gives, okay? So we created some model. Let me just skip some of this. So Chirag Chawla created very realistic models of the Milky Way population of black holes, and he predicted that Gaia, by its end of mission, will be able to astrometrically resolve almost 1 million white dwarf binaries several thousand neutron star binaries, and a few hundred black hole binaries. And roughly about 1/3 of these black hole binaries will have astrometric mass measurements good enough to put them above, say, 3 solar mass. So that definitely puts it to the black hole region. Okay. The nice thing about these binaries is that unlike in gravitational waves, where you are only sensitive to the masses of the black holes, you do not have any idea about the progenitors. Here you have a companion. You know the distance to the companion, so you can model the age and metallicity of the companion. And the progenitor that actually created the black hole must have had the same age and metallicity. So it finally creates an avenue that can connect some properties of the progenitor to the properties of the black hole that you can observe. And of course, remember, this is only about astrometry. Once you have identified the candidates, you can then do a follow-up with a large number of telescopes, and it will be very interesting, I think. Another nice thing is that since the detectability of these black holes depends on the luminous companion properties, the intrinsic population of the black hole and the observed population of the black hole do not show a significant difference as a function of the mass of the black hole. So if you find a population of black holes this way, then you will have a good confidence that this population represents the intrinsic black hole mass distribution. All right. We have also started looking at, just give me one second. We have also started looking at when the star clusters actually form as a function of redshift and what their properties are. If you want to talk about that, we can talk about that later. So I will stop here and leave it.
Okay, thank you, Professor Kennedy, for an excellent overview of the formation processes of potential gravitational sources. So, questions? So, we will start with our previous invited speaker. We'll come back to come.
So, when you are forming binaries in the Asian disk, for example, so, the common envelope is still necessary, or can meaning because there is just already there. So your problem was that you have to somehow bring the binaries closer after they become black holes. So
it's not. So you can create black holes at your will, wherever you want, and then type 1 and type 2 migrations bring the black holes together. And black holes can get trapped in resonances. Black holes can do type 1 and type 2 convergent migration. Like everything that you learned about exoplanets happens.
Okay. But then there are too many possibilities to actually say that what is the correct model. That is where, because otherwise, if all those are possible, then you will end up producing a lot more binaries than we see, right?
Well, very, very large uncertainties remain. So, for example, how efficient are AGN disks in forming stars? What is the IMF for these stars? Do you form black holes there? How the black holes behave? So, frankly speaking, this has so many parameters that it's kind of hard to say anything that's falsifiable at this point. But so my take on this is if you find a binary black hole merger that has a very clear optical counterpart, then that will significantly boost this, because then these black holes are merging not in vacuum, in some medium, and then maybe accreting. Otherwise, there is no necessity to invoke AGN disks.
Okay, other questions? overview.
I have a question about the astrometry method you talked about. From here, we are seeing 2D projection of the entire system. So, what would be the mass to mass ratio of the black hole and the star to actually we can see a change in the star surface? Like the tidal effect has to be that much prominent, and also the star has to be that much big, so that we can actually see any changes.
Yeah. So it's so the funny thing is, so there are two things that matter. So one is the size to distance ratio, and the other, as you correctly pointed out, the mass ratio. So basically the Roche physics. Okay. And then how deformable the star is. All right. So, for example, if you have red giants or late-stage main sequence stars, these and in a really compact orbit, then you can actually have this. So, Chirag Chawla actually looked at what is the expected yield that will give measurable photometric undulations. So, from the relativistic beaming, then self-lensing, and then this tidal deformation. Each of these numbers are given, and you can just take a look. It's a non-negligible number. And in fact, already from DR3, there are astrometric detection of compact object binaries, and there are also photometrically detected candidates. But the problem with photometrically detected candidates is it's not easy to verify what's the nature of the compact object. So, but a lot of effort is going on. This.
Another question.
I wanted to ask what is cosine mechanism?
So imagine that you have an inner binary and some perturber that is also in orbit around the inner binary, okay? And imagine a situation where there is no significant energy exchange between the inner binary and the outer binary. So that basically means it's a secular system, okay? So things are happening on much longer timescale than the orbital timescale. So if you calculate the orbit averaged effect of this orbit to this orbit, there will be a periodic exchange of angular momentum between these orbits. And the result of this exchange of angular momentum is oscillation in eccentricity and the relative inclination. Okay. So using this, imagine now that you have a black hole inner binary and some perturber. Typically, it's also assumed to be a black hole, but it doesn't have to be a black hole. Okay. So imagine that something is periodically making it very eccentric, this orbit, and not changing its semi-major axis because that's the energy exchange. Okay. So at some point, the pericenter will be so tiny that maybe there will be a burst of gravitational waves and then it will merge. Maybe it will just get just merge and come within the short shell radius and so on. Okay, so that's a very effective way to create a very, very high eccentricity merger in the LIGO band.
Other questions? Yes.
So from what you said, there doesn't seem to be any excessive general relativity in these calculations.
Oh no! Without general relativity, they will never merge.
But the description doesn't require.
The star cluster dynamics does not much care about gravitation, general relativity, because the typical distances are rather large. Where you have to at least take PN corrections into account is during the strong encounters involving black holes. So there, since these are the so-called resonant type interactions, these black holes can repeatedly come very close to the other black holes, and it essentially samples the whole phase space available to it. Okay, and there, yes, you have to take that into account, and we do.
You use the numerical relativity results about the mergers.
Yes. So for our n-body calculations, numerical relativity is a bit too expensive. And remember, there are millions of these binaries, right? So we actually use up to, I think, 3 PN terms. We can, but we decide how many terms to keep in a particular simulation. But the general relativity calculations we take into account to figure out, once the two black holes merge, given the angle of merger, like basic kinematics and the initial spins, what should be the final spin and what should be the recoil speed. That's coming from relativity. Yeah. Right.
Okay, thank you.
Okay, other question, there was a question from one of the.
Okay, so when these binary black holes form at the centers of the globular cluster, there must be some probability of 3 black holes or 4 black holes forming a closed gravitational bound system. So is the probability of binary formation much larger than this?
Yes. So we have done this calculation, and we do keep track of the triple formation. So the results on the triples and Kozai-Lidov things that I was showing, that is based on that. So in our normal simulations, we actually break the triples. We take a triple, we analyze whether it's an interesting Kozai-Lidov system or not. If it's not doing something interesting, it's actually very, very expensive to keep the triple, because then the size becomes so big, the interaction cross-section becomes too big, and it doesn't do anything interesting. So
By hand you break it.
by hand we break it. We have tested, and the condition of breaking that we have and the energy distribution that we adopt is correct, is validated based on n-body results, where the dynamics actually goes and breaks the triple.
No.
Yes,
I-
one last quick
I think there was a question
from-
there.
Curious to know that about you have very what conclusion or whatever on the PBH primordial black hole module to form the black hole.
It's possible to do these simulations if you can tell me the mass distribution and the dynamical properties that you want. I have not done it. So the usual way that we think about it is, so there is some star formation rate over cosmological redshift. There is some cluster formation rate. Both of these have some uncertainty. But then the primordial black hole formation will peak at even higher redshift. So the reason why we have not tried doing a dynamical simulation is because these primordial black holes are expected to be in a collisionless system because it's many and not very dense. So it's better to do the simulations as a cosmological dark matter simulation, not a collisional star cluster relaxed system type simulation. But people, I think, have thought about what cosmological halo formation can mean to primordial black hole merger and so on. And the major uncertainty is what is the mass of the primordial black hole.
Okay, so I think we will end the questions here. If you have further questions, you can talk to Saurabh in the break. You have to go to lunch and come back for the next session. Quickly, our MSc second year student Shalini Kundu will give a token of appreciation to.
Thank you so much. Thank you.
Okay, so we will have lunch next door, and then come back here at 2:30 to start the next session.
So that's next door, and then there is a room open Beside the lunch, look where we'll go and have that. So here we have.
So you'll have 8 minutes and I'll give you, so Shomodev, I'll give you a reminder at 6 minutes when you have 2 minutes and you'll wrap up in 2 minutes, okay?
Sure.
video panel.
This is the one. Presentation, right? Everything's perfect.
Sound is on.
Sound, yeah. So this one. This one is not working.
No.
Battery doesn't. Battery. It's on. Yes. Yes. The controls.
Fine. Hello. I hope you can hear me. Okay, so good afternoon, everyone. I'm Soumyadeep Vasak. So currently, I'm a postdoc at Science Institute of Nuclear Physics. So today, I'll be talking about the work that I did during my PhD. So it's about gravitational wave microlensing as a probe of compact dark matter, which was supervised by Professor Parameshwaran Ajit at ICTSTF Bangalore. So we know almost 25% of the mass energy content of the universe is filled with some sort of unknown form of matter, which is known to us as dark matter, that interacts only via gravity. So in what we assume is if a significant fraction of this dark matter is in the form of compact objects like primordial black holes, they will cause microlensing effects of the GW signals, which are potentially observable by live and Virgo detectors. So what we do is from the non-observation of these microlensing signatures in the binary black hole events, from the first 3 observing runs of LIGO Virgo, we constrain the fraction of the compact dark matter in this mass range 100 to 100,000 solar mass, where this quantity, FDM, is the quantity of interest. This basically talks about the fraction of compact dark matter. If it is 0, then no dark matter is in the form of compact objects. If it's 1, then every dark matter is in the form of compact objects. Fine. So this is basically a pictorial representation of what we are talking about. So there is this gravitational wave source which emits this gravitational wave. In its path, it encounters suppose a primordial black hole, which acts as a compact dark matter, which is the compact dark matter object, and this acts as a lens. This can actually potentially lens or microlens this gravitational wave signal, which is potentially detected or detectable by this gravitational wave detector here on Earth. So this is the gravitational wave signal, original, undistorted, or rather unlensed, and this is the lensed wave gravitational wave signal. So the idea is, if we do not see any lensing or microlensing signature of these signals, we try to constrain the compact dark matter fraction from this non-observation or microlensing signature. So, but how do we quantify this lensing signature? For that, we use this Bayesian model selection technique. So here we define something called the odds ratio, which is the ratio defined basically to distinguish these two hypotheses: the signalist lens, the other, and over the signal being unlensed. So this is the quantity of interest odds ratio, where we try to find the support of these lens hypothesis being true given the data over the unlensed hypothesis. This can be further decomposed into two other quantities. The first one is called the prior odds, and the second one is called the Bayes factor. So for the lens, for the signals to be lens, this quantity should be much greater than 1, or in terms of Bayes factor, they should be much greater than 1. So when we do the Bayesian analysis to the gravitational waves on the gravitational wave signals with the first three observation runs of LIGO Virgo, where we detected 54 gravitational binary black hole gravitational wave events, and what we find is the maximum of log Bayes factor is around 1.15, which is shown here. And that doesn't necessarily support, or this basically says there is no compelling evidence of macrolensing on any of the gravitational wave signals. So using this idea that we have seen no gravitational lensed gravitational wave event, given that total 54 gravitational waves were detected and no lens signal was observed, we compute the posterior on the Poisson means, lambda and lambda. Let me describe what these things mean. So here we assume that the processes of binary black hole events, the detection processes of these binary black hole events, as well as the lens processes, follow a Poisson distribution, a Poisson statistic, which are characterized by their means lambda and lambda L. And the left side of this plot, we have shown the posterior distribution of this lambda mean of the detected events, and the middle plot shows the posterior, similarly the posterior distribution of lensed events for the lensed events. And when we if we can derive the posterior distribution of these two, we can derive the lensing fraction as which is defined in this way. And the right hand side of this plot shows the posterior distribution of this lensing fraction. Fine. So this is basically a data-driven quantity where I have shown here the same thing. I've described the same thing. Let me remind you this thing that we, from the first three observing runs where we detected 54 GW events and none of them was found to be lensed, we derived this quantity, this lensing fraction. So if we know that this quantity, then we can translate using this equation, we can translate this posterior distribution to find the posterior distribution of this of the quantity of interest, that is FDM, or the compact dark matter fraction, given the same data. But here comes this extra sort of thing that is we need to derive or establish. This is the search sensitivity. This is called the Jacobian. But how do we get this Jacobian? For that, we generate a population of binary black holes to find the detectable lensed events. So for that, we simulate a population of binary black holes following some astrophysical models, and we assume these compact objects are distributed uniformly in co-moving volume. And from that, we compute the fraction of detectable lens events, that is those events which cross this threshold 1.15, that comes from the real data analysis, the data analysis or parameter estimation from the real events for different values of this compact dark matter fraction. And yeah, I'll like 2-3 slides more. So this is a plot for this Jacobian actually. So in our simulation, what we have shown here, the lensing fraction as a function of FDM for different source redshift distribution models, and we have assumed monochromatic lens masses for 100,000 up to till like up to 100,000 solar masses, and this plot shows the lensing fraction as a function of FDM. Fine. So if we know these two quantities, this Jacobian as well as the posterior distribution of the lensing fraction, we can use these two quantities to translate the posterior on FDM. In this plot, we have shown the posterior on FDM for these two different choices of prior. Because we are talking about posterior, we need some prior information. But again, for these 4 choices of lens masses, 100 to 100,000 solar masses. And this is my final plot where we have shown the exclusion plot of compact dark matter fraction as a function of the length masses in the mass range 100 to 100,000 solar masses. So this plot basically shows that these regions are excluded from our analysis. And what we have found is we can put bounds on this FDM or this compact dark matter fraction is somewhere in the range 50 to 80%, given that we have seen only 50 gravitational wave events and none of them was found to be lensed. And this is our current work, which is in preparation, where we have tried to put future bounds on the compact dark matter fraction. But it's an extended analysis, actually. This work is in progress. And here we have shown that this is a very significant improvement on the FDM quantity, which is around 10 to the power minus 3 or 1 in 1,000. And these are some of the constraints coming from the electromagnetic observations. And with this, I thank you all if you have any questions.
How did you choose the likelihood, for the microlensed events?
Likelihood in the sense like
Given the parameters.
So
Meaning the reason I'm asking is
yeah. So I have a slide actually for that. So you have this this is the unlensed, or let me show you in the time domain plot. This is the gray color shows this unlensed signal, and for different choices of lens masses, we have shown the gravitational wave form for or the lens gravitational wave forms. So what we do is do the parameter estimation for these two hypotheses, unlensed and lensed, where by lensed we introduce this frequency dependent magnification function on this unlensed waveform. So with this we do this parameter estimation.
Okay, time for one more. Any other question? Yes, sir.
I'm not an expert in this, but what are the degeneracies, possible sources of degeneracy?
I mean, with lensing, with some other thing, one can be with this, what do you call this, eccentricity thing, where someone has done similar work where they have shown that there can be a possible degeneracy with between microlensing and eccentric waveform. And we haven't done that explicitly though, but there can be in principle. As well as there is a degeneracy also between these two like parameters, this lens masses. Sorry, it's not working again. This lens masses and the y, this parameter, this is called the dimensionless source position. They can be degenerate with each other. Thanks.
Any other question? If not, let's thank somebody.
Thank you.
So our next and final speaker of the session is Ms. Afrik from Shah Institute of Nuclear Physics. So you have 8 minutes. I'll give you a brief reminder and then.
Hi everyone. So I'm host of SIMP, and my talk today would be a bit of an outlier, in the sense that I would be speaking about different incentives, speaking about convenience of dark matter through photons, and for that we'll be considering dense photons around supermassive black holes sit at the galactic centers, and they serve as one of the strongest gravitational lenses. So I would say that we are in an era of multi-messenger astronomy as well as cosmology, but yet the dark matter remains as elusive as ever. And we are constantly trying to develop newer and independent probes different centers to better understand dark matter. So one of those probes is the black supermassive black holes, which have been recently imaged or photographed by the Event Horizon Telescope collaboration, and it's one of the first direct evidence, I mean, after light approach of supermassive black holes and black holes in general. So the black holes event horizon actually captured not only the intrinsic space-time information like various hair parameters and variations media, but also they capture surrounding matter energy profiles, which does not only include ordinary matter, but also exotic matter, including dark matter. So, these images in black hole basically lensed event horizon images, and which we call loosely as a black hole shadow. I will go into the detail of what actual theoretical shadow is. And the question we pose today is, can the event horizon scale images of supermassive black holes like M7 star and Sagittarius star capture the presence of dark matter at galactic center and constraint? So when we considering dark matter evenly coupled to gravity, where the dimension is been seen, and the energy of metal tensor consists of two parts. First is the ordinary matter, another one is the dark matter. We consider the surrounding dark matter to be a perfect fluid, for which if we considering an equation of state, it actually comes from phenomenology using Alex simulation curves. We find the strength metric PFJ and black hole metric. We know that this is completely similar to Schwarzschild black hole, and with the dark matter parameter K over here, which is an integration constant, seeping into the mass function. Find the rotating counterpart of this, which was the rotating BFG black holes, and these black holes are in a curve-like form, which again the delta they having an extra. So now regarding the messenger, as I said, we will have to know how the photon actually carries information from the galactic center all the way to our telescopes. For that, we have to understand the photon's path, or what we call the ray traced path. So that will solve the second order derivative equations. The four of them will be giving 8 initial conditions. 4 of them would be the initial coordinates, and luckily for us, we have 4 other first order differential equations which come from the space-time symmetries, which are similar because of the third black hole. We have you can consider a very special class of photons, which are the spherical photon orbits, which have fixed orbital radii around black holes, because these are the photons which populate the outline of the shadow. So we find them from this radial turning point equation, and from there we can solve the angular momentum, the energy normalized angular momentum over here, which is the xi over here, and the energy normalized Stark constant, that is the eta. And we get 2 classes of spherical photon orbits, the appropriate retrograde as well as zero angular momentum photons. So we can retrace the photons. This is one complete theta oscillation. We saw that the starting and the ending point of photons differ by delta phi angle, and the characteristic feature of the presence of dark matter is that delta phi changes with the increase in the dark matter. Over here, it's 0.4, 4, and over here, the dark matter parameter is 0.6. So, we can retrace the photons. This is one complete theta oscillation. And we saw that the starting and the ending point of photons differ by delta phi angle, and the characteristic feature of the presence of dark matter is that delta phi changes with the increase in the dark matter. Over here, the dark matter parameter is 0.4, and over here, the dark matter parameter is 0.6. Now, an interesting fourth class of photons was recently found by Ron Gage and for a third level, wherein they showed that if we, for a particular spin of the black hole, if we choose a photon perpendicularly from the north polar axis, then the photon comes back exactly in the opposite direction, and that's called the boomerang photons. And what we found is that the boomerang photons are only found in GR for the current case only around black holes. But if the dark matter diameter slips in, we can begin to get these boomerang photons for naked singularity as well. Over here, for the third black hole, this is for the Pleiadian black hole, and this for the Pleiadian naked singularity. So, this doesn't have any observable simulation yet because we haven't studied them yet. But once we study them enough and we are able to find out, we will have a way to distinguish between black holes and naked singularity. So why these photon orbits are spherical photon orbits are important is due to the fact that all the collection of the spherical photon orbits for what we call the spherical photon shell, which is a 3D region around the spherical black hole, and each photon from this shell, it makes a number of rotations on the black hole, hits the observer screen, and if we trace out all those photons, we get this what the shadow critical curve, and we know that this XY movement of the shadow, they are dependent only on the black hole's intrinsic parameters, including the dark matter parameter, and one extrinsic parameter which is the information angle of the observer. So with that, we plotted the black hole shadows. This was just outer one is for the third black hole, and as the black hole, as dark matter parameter seeps in, we see the shadows getting substantially smaller as well as distorted on one side. This is the prograde side. This behavior is similar to what we see in a curved black hole shadow. The spin increases and we observe it at a higher intensity. So,
so that
okay. So, we use various observables, shadow observables that the PhD has measured, and one among them is the Gaussian deviation, which is the fractional deviation of a model that is diameter to that of the Gaussian diameter. And for ME7 and Sachet, these bounds have been observed. And one point is that the curved shadow may also deviate from that of the short shadows for diameter, and this can be by at most 7.5% as the spin and the inclination angles vary. So it's not that this value could be constant even in GR. This could depend on both the spin and the inclination. But please note that this PhD inferred bounds, they are much wider and they contain this region. And what this means is that outside this region also, we can get black holes which cast a shadow that do not contradict the PhD findings. So you see that with the bound on our parameter space, the spin and the black hole parameters, spin is not constrained, but the black hole parameter is. It's both modeling the MH7 star and the Sagittarius star as black holes, and we have found some first something from the PhD parameter from Sagittarius star, and continuing on this line, the PhD is at a very nascent stage at the moment. So there are a lot of data. So as we develop experiments like the next generation PhD and even space area, we are not only looking at the black holes critical curve, but also lower order photon rates, and that will probably give us much better constraints.
One question. one fast and one